Yeah. Are you on this? You just can. Are you on the cannot? If not, can you write down your ID and your
In the key section.
Okay.
Yeah, this one.
Oh, this one?
Yeah.
Okay, I will add you. You just can.
This one.
Testing. I have enrolled you. You can check out. Okay, welcome back. Um, we have this math health center working on Tuesday, Wednesday, Thursday, Friday, 2 to 4. If you can't come to my office hour, you can get help from the center. I think so far only 3 person come to my office hours from your class. Yeah. Okay. Any question before we start the lecture for last week? Q&A section. Any question? And I want to remind you, next week is our first quiz. Okay. If no accident, we will hold the first quiz next week. Okay, no question, then we're going to today's lecture. Okay, before we start, we revise what we did last week. So we did topology, which is a compound proposition that's always true. And we also have contradiction. We also introduced contradiction, the compound proposition that is always false. And we have some examples and prove the general statement. Okay. showing that the compound P or not P is a tautology, and sorry, P or not P is a tautology, and P and not P is a contradiction. Okay, no problem. And then next, so this is what we're going to introduce today, logically equivalent. Oh, by the way, I want to remind you today might go quite a bit fast, so please catch up. And stop me if I go too fast. Okay, two compound propositions P and Q are called logically equivalent if and only if Q is a tautology. Okay. Another practical way to check is to check that P and Q have the same truth values in all possible cases. And it's a good exercise that to show that these two are actually equivalent definition. Okay. So that exercise. Show these two definitions are equivalent. Okay. Okay. So let's look at the first example. We'll have not P or Q is logically equivalent. This is the logically equivalent notation. 3 line. It's logically equivalent to not P and not Q. Okay, so you bring the not into the compound proposition, the or become an and then you negate both statements. Okay, let's try. So I already have this truth table ready here. So what's P or Q? True, 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 false. How about this line? False, 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 true. Not P and not Q. False, 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 true. And then how about this? If only if all true, 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 true. So okay, so you see, so I have checked. So this is the label. This was so this is 1. This is 2. Okay, so this is the first method. Not first method. I mean, coming from the first definition, and then this one is coming from the second definition. So you show that P if and only if Q is a tautology, or you show that they have the same true value in every possible cases. Okay, exercise is to show these two definitions are equivalent. Okay, so today you have to memorize this before you become a logic student. Okay, so this is called a De Morgan's law. Okay, De Morgan's law. Actually, De Morgan's law has another variant, which is not P and Q is logically equivalent to not P or not Q. Okay, exercise, show at home. Okay, so you bring the not into the compound proposition and you n become or, and then also you negate the both statement. Okay, this is left as an exercise. Any question? No? Okay, next. So next, this table, somebody asked me what need to memorize or not. No need, but you have to understand what is going on. So this table is actually not too strange. It's actually quite familiar with you if you remember your number system or maybe algebra. Okay, so you can think of all as a plus and as a multiplication. Okay, so in plus you have 0, so anything add to 0 is 2. In multiplication you have 1. When you multiply with anything you get that itself. So these are called the this in this case is the additive identity. And this case is the multiplicative identity. Similarly to logic, so when you combine two propositions, you get back yourself, then this is an identity. Okay, so P and a true, this is a true, always true statement. So this is an always true statement. True statement. You get back your original statement. If you take a disjunction with a false statement, then you get back your original statement. You can show it using the truth table as well. Use the previous method again. So you draw table for P and then P and T. T is always true. And then you show that it have the same true value with P. Okay. Domination loss means if you combine with T, for example, P disjunction with T, you always get T. Okay. P, the true statement dominates over the original statement, or the false statement dominates over the original statement. So that means if you have some proposition and then you said something that is always wrong, then the whole thing is wrong. The whole thing is just wrong. Okay. But if you have some proposition and then you tell that or some true proposition is always true. There's nothing to do about with your other proposition. Okay. Okay, idempotence law. Idempotence law is something like a squared to a. So it's squared to itself. So it's called idempotent. So in this case, so if you take P, disjunction with P, you still get back yourself. And then P, conjunction with P, you still get back yourself. Also in the double negation law, you have not P is P. So actually I secretly used this last time in the last lecture. So actually you need to show that not P is P. We will do this in tutorial later as well. So this is also not too strange to you because we have like minus 1, for example, equal to 1. Okay. Commutative laws, so you can commute them. So also like the number system, you can commute your addition. And associative laws, we touched a bit last time, so it's the same. You do the first, and then you do the all, and then you do the last one, and then you go out. Okay. Distributive law. So distributive law is like in number system, you have like 2 times 3, something like that. So it becomes 2 times 2 plus 2 times 3, something like that. Okay, distribute. And De Morgan's law, we touched on it just now. Okay. Absorption law. Okay, you can look through this. So absorption law may be useful to like reduce the condition in your coding or what. Okay. So you see P or not P or P and Q is actually just P. So nothing to do with the Q. Also, this negation law we already proved it last week. P or not P is tautology, always true. P and not P is always false, contradiction. Yeah, this one we proved it last week. Okay. If I want you to use in the exam, maybe I'll provide you the law, but I won't tell you how to use it. Okay. Okay, this one is very important because this connects the implication, the conditional statement with the disjunction or conjunction statement. Okay, so maybe we'll do it later, but make sure you know this line. Okay, this line you must know. P implies Q is logically equivalent to not P or Q. And also this line, what is this? Anyone can recall what is this line actually? What's this statement here? Not Q implies not P. Contrapositive, yes. So this is the contrapositive. So if you want to show P and Q is true, you can show not Q implies not P. Okay, this one is very useful. And then the others are all derivation from these two. And another one is, this one is quite important. So this connects the double-headed arrow to one-headed arrow. So this one I also talked a bit last week. And what is this? Can you recall this? What's this? Q implies P. P implies Q. Converse, right? Yeah. So if you have P implies Q and it converse is true, then you can have P if and only if Q. Okay. Yeah, the other are just derivation. Okay. Let's try this. So we want to show that P implies Q is logically equivalent to not P or Q. Okay. So we want to show that these two have the same truth values. Okay. So let's look it up. Um, P implies Q is what? True, false, true, true. Not P or Q. True, false, true, true. Okay. Okay. Good. So we have the same truth values. So this means by definition, they are logically equivalent. So next, I have this question. So let you try. You can discuss with your friend. Spend 2 minutes. See how to show the logical equivalence. Are you okay or not? Are you okay or not? Is it too cold? Is it too cold? Okay, let's see. What have you done? Anyone can share what have you done? Huh? What have you done? Use truth table or what? Truth table? Okay, what's truth table? Like that. So you draw a truth table. Okay. So you label P, Q, not Q, not P, implies Q, not Q implies not P. So you have true, 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 false, false, true, false, false. So not Q is false, true, false, true, not P is false, false, true, true. Implies Q is true, false, true, true. Not Q implies not P is true, false, true, true. Okay, but there's another method. Anyone try this algebra method or not? Using the table just now. So P implies Q, like before, we know that it's logically equivalent to not P or Q. Right? And then since disjunction commute, you can do this. This is the no. Okay. And then we do the reverse definition again. So it becomes not Q. Okay. Yeah, sometimes depends. Sometimes algebra is faster. Sometimes you can do truth table. Sometimes you must do truth table, for example, this one, because we haven't show this. And then this, I assume you already know. Of course, if you want to convince yourself, make sure you do the exercise first. Okay. Any question? No? Next. Huh? Any question? Any question? Fun. No? Okay. The third one, I will leave it as an exercise. So go ahead and try P if and only if Q is logically equivalent to P implies Q and Q implies P. If we have time, maybe we can come back, but I will leave it as an exercise now. And go into the next section. Okay. Okay, next. Okay, next. So let's go into the next section. So now we want to introduce variable into our proposition so that our proposition will contain more information at once. Okay. So we will introduce a thing called amplifiers. Let's give some definition. So let Px be a sentence. Yeah, just a sentence is enough, no proposition. And this sentence contains the variable x. Again, we call P a predicate and x subject. If the sentence consisting P and x is a proposition when x is specified. Okay, remember last time we talked about x plus 2 equal to 5 is not a proposition, but when x is specified, then it is a proposition. Okay, remember from last week, correct? And this x supposed to live in a space. Okay, we call it a set. The set that x lives in is called the domain of discourse or domain. Okay. So this x will live in some space. Okay. because we haven't do set theory yet. Set theory will be in the next chapter, next topic. So now you can understand it as a, let me write down, collection of objects, or you can think of it just as a space. For example, you are sitting in the classroom now. So classroom is a space. Okay, a space. Next, next. So example. So suppose X is in Z. Okay, this I need to introduce you first, and then later we'll see more example. So these are integers. So integers are like negative number, positive number, positive, negative whole number. Okay, and then suppose X, and then the statement is X greater than equal to 0. Okay, so in this case, Px is X greater than equal to 0. Okay, this is the sentence. We can say it is true or false, right? Based on last time what we discussed. But, okay, and then this is the subject itself, and then this is the predicate. Okay, so let's see what is P1. So P1 is 1 greater than or equal to 0. Is it true or false? False. True. Okay. How about P minus 1? So P minus 1 is minus 1 greater than equal to 0. True or false? False. Because minus 1 is less than 0. Yeah. Okay. Yeah, now I want to introduce some examples of domain so that we know what kind of space we want to use. So first, the natural number. Okay, the natural number is 0, 1, 2, 3, 4, and so on, 5, 6, 7, and so on. Some people don't include 0 as a natural number because they say humans start counting from 1, not 0. But I just include 0 because there's a yellow axiom that construct natural number starting from 0 and then using the empty set. Maybe I'll talk a little bit more when we introduce set theory. Second, we want to have the integers. Okay, integers. So integers, we also have the natural number, but we have the negative version of them. So negative 1, 0, 1, 2, and so on. So these are introduced because when you add the natural number, you can only go larger and larger and larger. So when I introduce the negative counterpart, then they can cancel each other and then go back to 0. The third one I want to introduce is the rational numbers. Okay, the rational number is the fraction of uh, integers, and n cannot be equal to 0. Otherwise, divide by 0, you will get undefined. So, for example, you have the fraction. Okay. Also, you will have the integer. Also, you have the number. Okay, fourth is the irrational number. So this irrational number I will write as the I1 for the moment. So these are like both and again both that bold, and then Q bold. So irrational numbers are the numbers that cannot cannot be expressed as ratio to integers. Okay, for example, what the time, the e square root 2, and so on. Okay, so actually there's a story attached to this square root 2. So during the Greek time, so Greek time we have this. I think you are quite familiar with Pythagoras. Pythagoras theorem. Anyone know what is Pythagoras theorem? Is on ah, anyone know this? A square plus b square equals c square. So during the Greek time, they are interested in geometry. Okay, interested a lot of in geometry because maybe it's because of their politics. They need to divide their land properly. Okay, so a square b square equals c square. So if you look at this right angle triangle here, what's the hypotenuse? Square root 2. Okay, so they spend a lot of time finding what is square root 2 because so Pythagoras is a mathematician, right? So he go to school, so all the students will be called Pythagorean. So they love mathematics a lot, and then they think that mathematics is perfect, is beautiful. So every number should be like rational number, can be expressed properly. But this irrational number, they cannot be expressed as a rational because there's no pattern for the decimal expansion. Okay. Quite a few mathematicians counted this around the world. They expand up to maybe 1,000, 10,000. Even mathematicians from China also working on this. I mean, working on pi. Pi. Pi is also another story. They show that it is irrational. But in this case, square root 2, actually there's an elegant proof by contradiction that square root 2 is irrational. And then somebody showed it to the student of Pythagorean, and then they killed it because they don't believe that square root 2 is irrational. So, and also this is the first proof I learned in the pure math class. So we should see it once. Okay, maybe we'll do it next time. Okay. Proof by contradiction that square root 2 is irrational. Okay. Okay, so that's that story. Then next, um, fine. So this together, rational with irrational, we have the real numbers. Okay, the real numbers is the rational plus the irrational. So this is just union. For now, you just understand as I combine the rational and irrational numbers. And then 6 is the complex number. Yeah, complex number, I think you have touched it a bit during your preview or someone. Okay, for these numbers, right, what I want you to know for now is what kind of number exists in this set. Okay, so if I talk about integers, you should know there are these numbers inside there. When I talk about rational, these are the numbers inside there. real numbers, all these numbers will be in there, and then so on. And maybe some terminology. So we will have positive integers. Positive integers would mean numbers that are greater than 0. Negative integers are number less than 0. And we also have non-positive integer, which are number that are less than or equal to 0. And also we have non-negative integers, which are number greater or equal to 0. Okay. Okay. Next. Okay, next we'll have some quantifier. So we introduce the universal quantifier here. So we call a universal quantification of Tx. For Tx itself is not a proposition, so we need some quantifier for the x. So this is what is the proposition for all values of x in the domain Yes. Okay. So one way we can write it is for any x in the X written as for every. So let me put some comma so that people show. So for every x d. So this x is an inverted a. Okay. So in the old time, there is no computer yet. So they use a typewriter and I do dot and then put it in. So they just pull out the button and then they turn it, they invert the A button and then they type. So this how this A get invented. Okay. So invert the A for all. So they take this A and then inverted it. Okay. And then define. So this inverted A is called the universal quantifier. Okay. So there are a few ways to talk about for all. So we can say for all, for every, for any, okay, givens x, and then something works. Okay. Yeah, example. For example, for every x in R, yeah, real number, x plus 1 is greater than x. True or false? Huh? True or false? True or why? Why? Huh? Say again. It's always greater than. It's all it, no, I mean, I want you to prove this, right? I want you to prove it. Like 1 plus 5 is greater than. Okay, this is good because this is an example to help you to understand it. But I want you to prove it now. Prove it. How to prove? Huh? How to prove? Hmm? Any idea? Who? Who is talking just now? Any idea? How to prove? Adding 1 is always greater than x. Huh? Any idea? Any idea? Mathematical induction. I think too advanced. Mathematical induction can, but I will touch on it next week. Mathematical induction. This is a simple way. Simpler way. Ah, because 1 is greater than 0. Okay, so 1 is greater than 0. So you just take any x in R and then add it on both sides. Okay. So note that this is different. This line is different from this line, okay? So this says that it works for every x. This, I take a particular x. So I want to make some notes here. This is a particular x. Okay. So when I say particular x, you should imagine in your mind this x could be your favorite number is like 2, maybe 2. So 2 plus 1 is greater than 2. Okay, or 0.5 plus 1 is greater than 0.5. Okay, so this is a particular x, and then you do it for all x. Okay, it works for all x. Okay. Yeah. Okay. And next, definition. So a statement for every x, x. So if you want to prove that this kind of statement is not true, you need to find an x in the domain when x is false. Okay, then such an x is called a counterexample. Okay, so we already encountered this in the first lecture. So if you remember, every number greater than 1 is less than a million. So the 2 million is called the counterexample. Oh, sorry. Mathematical induction doesn't work in this case. Because you know why? Because this is a real number. So usually mathematical induction will induct on integers. I mean, real natural numbers. 1, 2, 3, 4, 5, 6, 7. Usually it's a plus 1. But this one is a real. So that is like discrete. That is discrete. But real number is like continuous. Real number is continuous. So yeah, there's a topology on real number. Non-trivial topology. Anyway, but next. So we define the existential codification of Px is the position values and element x in the. Notice that I always say that x in the domain of something, right? So make sure this x, how to say, I know where to find the x. So you always have to tell me where this x live in. Okay, in the domain, in some domain, what domain? So every time I have to tell you, when I say about X, I have to tell you what is the domain it live in. Okay. So the notation is shortcut. Notation is the inverted capital E. Okay, there exists. So inverted capital E. Yeah. So the definition, so we call this existential quantifier. Existential. Okay, so there are a few ways to say about it. So there is this, or there's one. Okay, or we can find some X such that it is true. Find some. We can find a few. We can find one. Find one. Find a few. Find some. And maybe find one is okay. Maybe find some. A few, maybe too many. One is enough. One is enough to justify the existence. Okay. One is enough to justify the existence. So, for example, there exists an X in R such that S squared equals to 2. True or false? True or false? True or false? True. Why? True or false? True. Why? Why? True or false? Can you find an X in R such that X squared to 2? True or false? False. Someone said false. Tell me why is it false? I want to know. Huh? True or false? Why is it true? Why is it true? And you cannot simply tell me true or false and then don't tell me reason. True or false? Huh? Sleepy, sleepy. I identify two person here. I always sleep one in my class. Sleep until you say classroom is better to sleep than the. Hey, true or false? True. Why? Why? Square root 2, Yeah, square root 2. Yeah. Why take so long? Square root 2, right? True. Okay. Square root 2. Okay. X equal to square root 2. And x squared is 2. Okay, actually not just square root 2. You also can take minus square root 2. Okay. So in this case, actually there are two examples. I mean not two examples, I mean two solutions. Two solutions to this polynomial. Because this is degree 2, right? So you have two roots. Next, there exists an X in R such that S squared equal to minus 1. True or false? Why? So you say, huh? Where is the three? What? Three is three. Three what? Three. Three. What? Find the elemental side is where is we what like that. We can find the number in the where it 不能找我都找不到，找不到这电话的 MP。哎，你不听吗？怎么你讲还以为听不到你讲什么？负英里哦，negative one，不负一两个词，OK。No，OK，没有，有没有解释到？有没有解释到？你还是在重复题目，所以我不要你重复题目。I don't want you to repeat the question, OK? I want you to um I want you to I want you to explain why you can't find okay, wait. You can't find a number which is square to minus one. Real? Okay, and then so say again louder, huh? Why? You're also repeating the question. Why? This is what you want to prove, right? So why? What? Mm, yeah. Yes, very good. So when you square the number, yeah, very good. So when you square the number, it's always greater or equal to 0, okay? Which is greater than minus 1, okay? So it's never equal to minus 1, okay? And this is true for every x. Okay, good. Okay, so this is false. And actually, this is the birth of complex number. Okay, so the algebraic person, they want to solve this polynomial by adding the root called I squared plus 1 equals 0, which is I squared equal to minus 1. And then this number system already proven very useful, especially in the area of electricity, electronics. Okay. Okay. Hey, what time is it? Okay, 9:50. Let's have a break for 2 minutes and then we'll come back again. Okay, I'll pass the attendance, please. Okay, next. So, in summary, what we have is, so for every x, px, when you want to prove that something is true, you need to prove it for every x. Okay, test it for every x. Then when is it false? You need to find me an x such that px is false. Okay. So for there's this an x px. When is it true? You just need to find me one. One is enough. But when is it false? You need to show me for every x. It's false. So sometimes it's easier to show for every x, yes, it's false because you just need to find one false is enough. And there's this one, you just find one is true. Okay. So let's try this example. So proof or disprove that there is an x in R positive s cubed is greater than equal to x squared. Try spend 2 minutes. Try out yourself or you can discuss with your friends. Proof or disprove s cubed greater or equal to x squared for x non-negative. Okay, let's try. Huh? Let's try. So if you want to show that it is true, then you need to show it for every number, right? So let's try x equals 0. Does it work? 0 greater than equal to 0. So it's true, right? How about x equals to 1? Also true. X equal to 2? Also true. So do you think it's true? No? Okay, wait first. So if you want to show it is true, you need to show it for infinitely many numbers. So you think it is false. So why is it false? Huh? What? Between 0 and 1. Wow. So fast give me the range already. Quite good. 0 and 1. So it just gives me maybe x equal to 0.1, then 0.5 is less than. Okay. So how to prove it in general? I think I think this algebra way is what you have seen in high school, right? So what you did is you looked at this less than 0, and then x squared, x squared, so this, and then you found the root, and then you put something like this, and then you put possibly, right? Yeah. Right? So this one you do, right? So you want x in between 1 and 0, right? Remember this? Is this how you found the range? Yeah. Okay. And but the way I think of it is using this way. So I will plot the graph or sketch the graph. So sketch the square graph, and then sketch the y square. And then set one. This one. Okay. Yeah. Yeah. Very good. Any questions? No. So to disprove it, you just need to find me one contact example. Is enough. Okay. If you find me a range, even better. Okay. And next, definition. So this is the uniqueness quantifier. Yeah. So sometimes there's only one that exists and a unique one, and we will write it as E exclamation mark. There's only one, so it's very excited. Proposition. There's this unique x such that px is true. Okay. So we'll write that there is this x in the domain. This one, forget the domain. In the domain such that px. Okay. And then we call this a uniqueness quantifier. Okay, this is quantification of a statement, and then the simple exercise is called quantifier. Okay, so there are a few ways to say it as well. So there's this unique one. Or there's this exactly one. Yes, exactly. There's one and only one. There's one and only one. Okay. So let's see some examples. So there's this unique x in R such that x squared, no, s minus 2 is 7. True or false? False. True. Why? S equal to 9. Yes, true. So take x equal to 9. Okay. So to prove it is unique, you just say that if x is not 9, then x minus 2 is not 7. Right. There's this x in R such that x squared equals to 2. So is it true or false? Huh? Why? Why? Okay, so already see it. You can take x to be square root 2 or minus square root 2. Okay, so next. So De Morgan's law for quantifiers. So when you negate statement with quantifiers, you will turn the existential quantifier into a universal quantifier, and then you negate the statement. Yeah. And similarly, you negate the universal quantifier, become a existential quantifier, and then you negate the sentence. So when is the negation true? Or when is this true? So you need to prove that for every x, px is false. Okay. And then how about this? You need to find an x such that ps is false. And then when is the negation true? You need to show that there exists an x. Okay, so you come back. There exists an x for px is true. And then when you want to show that this is false, then you need to show that for every x, ps is true. So logic is like this. So you go forward and backward, forward, backward. Okay. And you can prove actually these two are equivalent just using what I said just now. Any question? No? Let us look at some example. So not not for every x in R, x greater than or equal to 0. So using the De Morgan's law for the quantifier, not universal become not the universal become existential quantifier, and then not this become what? Okay, write this first. Okay, and then equal to, so logically equivalent to x. Become what? X less than 0. Okay. So if you realize that actually not less than equal to 0, it's actually not greater than 0 or equal to 0. Right? So we already learned that not disjunction. What law do you use? Right? What law do you use? What law do you use? Huh? What law do you use? The only law you need to memorize today. Huh? What law do you use to negate a compound proposition that have disjunction? What law do you use? De Morgan's law. So you negate both statements, and then you all become right. So then this one will become this, and then this one become that. Okay. So you want to show that this is actually x less than 0. Right. Okay. So there's a logic here actually. If you see there's a logic here, so let me insert this logic. So if I put p to be x less than 0, and then q to be x equal to 0, then p of q and not p is actually equal to p. This is something you can try and prove. Oh, this is like logically equivalence. Okay. You can try to prove this green line. T or not T, and not Q is T. Try to prove this. Okay, so put it as an exercise. Okay, and next. So for every, no, sorry. You want to negate, there's this an x in z such that x minus z equals 0. So you negate existential, what do you do? What do you get? Huh? Huh? What do you get? You negate this. Huh? Louder, not here. Huh? Universal amplifier, and then you negate the sentence inside. Okay, so 3 lines. So you get x minus 7 is not equal to 0. Okay, so when you see this, this is a proposition. Okay, proposition. So you need to be able to tell it is true or false. So is this true or false? Huh? True or false? False. Why? Who are talking? Who are talking? Are you talking? Yeah. It's what? When x equals 7, then to what? To what? True or false? No, it's okay, it's okay. You done? You finished? Or you still want to say? You done? No, don't worry, just say only. So it's false because when you found an x, when x equal to 7, x minus 7 is 0, which means this inequality is false. Okay. 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 How about this? Is this true or false? Huh? True or false? I mean this line, sorry, this line. True or false? Who's false, huh? True or false? Who say true? Who say false? True or false? Huh? True? Who say true? You? You are you saying true? Who say true or false? True or false? Wait, true or false? True. Why? Minus 1. Minus 1. Okay. So true. Because I can find x equal to minus 1, which is less than 0. Okay. Next. Okay. So this one you can do at home. So not for every x, px imply qx is there's this x, px, and not qx. So this is the combine of the quantifier version and the non-quantifier version. Okay. So yeah. So this is the De Morgan's law for the quantifiers, and then you use the, remember at the start how we link the implication to the disjunction. Okay, and then you take the negation. Okay, this is exercise. You can do it on. Next. Okay, next is called the nested quantifiers. So we have a few quantifiers together. So in this case, I want to show you the simplest example, which is just 2. In general, you can have more going on. So we want to see what's the difference between these 4. So we can take for every x, and then for every y. For every x, there exists a y. There exists an x. For every y, there exists an x. There exists an y. Okay. So this order is very important. Whether you take x first or you take y first is very important, because in general we will fix the one that comes first. So if every x comes first, then we will fix x first, and then we do y. This is called nested, because these are nested, these are nested. Okay, so we do this first, and then we do this first, and then we do this after. Okay, so for example, in this case, uh, also note that all these sentences are the same. Okay, x plus y equals to y minus x. So let's look at this example. It says that for every x in R and for every y in R, x plus y equals to y minus x. So you can, how to say, decode the sentence for every. So for example, it says that for every x, since suppose if it works for every x, then we can pick one favorite one. Maybe we pick 2. Maybe my favorite number is 2. So 2 plus y equals to y minus 2 for all y. So since it says that for all y could be true, so let's try 2 again. So 2 plus 2 plus 2 minus 2. So it's 4 equals 0, which is contradiction. So I already found a counterexample. Okay. Also, which means this is false. This sentence is false. Okay. But actually, there's a quicker way to check. So I introduced this for the sake of easy to explain. But you can try all these quantifier with this method. So actually, we can rearrange this equation. So what you have? So you have 2x equal to 0. X equal to 0. Okay. So actually, this 2 are equivalent. So this if and only if x equals 0. So exercise is, you can exercise is check the 4 propositions without the then you can do this. But for now, I will translate this sentence to x equals 0. Okay, so let's see. So for every x, there's this y such that x equals 0. True or false? Huh? True or false? True or false? False. Because if you take x equals to -1, then it is not 0 anymore. Right? So x has to be equal to 0. So it is not true for all x. Right? How about this? There exists x for all y such that x equals 0. True or false? True. Why? I can take x to be 0 and then y to be anything. 1, if I take y equal to 1, x still equals 0. If I take y equal to 2, x still equals 0. So I can take y to be anything. Okay? I can take y to be anything and then x still be 0. Okay, next. There exists an x in R. There exists an y in R such that x equals 0. True or false? Why? I can take x to be, y to be 1. Anything you want. So since the statement is true for all y, so that this y should be also true. Okay. Okay. Oh, pretty fast for this class. Everything turned into exercise very fast. Okay. Okay, rules of inference. Okay, this page is just for your information, maybe not so important, but if you want to talk about logic, maybe this will be important. So, so an argument, so you already learned a lot of statements, right? Propositions, so on. So if you put into a sequence and then end with a conclusion, this is called an argument. Okay. And when is your argument valid? Your argument is valid when the conclusion is true and whenever all the preceding statements are true. So it's like there's an implication one. So implication until conclusion the end is true. And then before the statement before the conclusion we call premises. So in your mind you should have something like this. So you got an argument. Maybe you got argument with your girlfriend or boyfriend, right? So now you got premises and then you reach to a conclusion. Okay. So if these things all hold, and then will imply that the conclusion is also true. If imply that conclusion is true, then the whole thing is valid. Okay. So incorrect reasoning are called fallacies. So if your argument invalid, maybe there's a fallacies inside. Okay. Okay, this next page is what I want you to know. So in general, when you have P implies Q, if you have P will happen, then you will get Q. Okay. So you will have Q. Or you have P implies Q, you have not Q instead, then you will have not P. What is this? This is the on what? On what? Contrapositive. Okay, this is contrapositive. So P implies Q is not P implies, sorry, not P. Not Q implies not P. So if you have not Q, then you will have not P. Okay. And then if you have P implies Q, Q implies R, then you will automatically have P implies R. Okay. If you have P or Q, and then you don't have P, so for this statement to be true, you must have Q. Okay. If you have P, then you can just disjunction with any other proposition. If you have P and Q, then you can deduce P or you can deduce Q. Okay. If you have P and Q, then you can have the conjunction P and Q. And then the next one is a resolution. We will have exercise on this later. So why are these true? Because you can show that the second column are all tautology. Exercise, make sure you do. Convince yourself. Okay. So if you have P and P implies Q, you will implies Q. Okay. Try do this. This is the how to say verification for this rules of inferences. Rules of inference. Okay, do this tautology and then convince yourself this rule of inferences. Okay, let's see. Yeah, let's see. So I must let you get this idea today. So when I first study this logic thing, I also keep thinking about different examples to convince myself. Also new for me when I learned it like last time. So let's see. Let's give this example. Let's see. So I define the negation of it. Okay, maybe just write negation of it. Negation of it is haven't it eaten equal. And then not who is hungry. Okay. So let's see this claim here. So I claim if I add n I'm full. Okay, so uh, so what I did, what I did, so I ate, so I ate. So consequence is what? So I am full. Okay, so I ate, I'm full. Yeah, let's say the second claim, if I'm hungry, and I haven't eaten, right? Right. So if I say I ate, then I'm full. If I'm hungry, then I haven't eaten. Okay, these two are equivalent. I say this is claim one, this is claim two. Maybe I claim another one, whether it's true or not. Do you think it's true? Let's say this is not true. I mean, this is implied or not. So let's see if this is implied. If I haven't eaten, then I am hungry. Do you think this three claim is logically equivalent? Huh? Which are these three? So the question are these three claims logic equivalent? Hmm? Yes or no? Yes. You think yes? You think yes? Can you tell me why? Tell me why. I want to know the reason. Seriously. Nah, nah.
Yeah. If I ate, I've eaten, then I'm full.
Okay.
Then not hungry, then I haven't eaten.
Okay.
Then if I haven't eaten, I'll be hungry.
So why are they the same? Why are they logically equivalent?
When hungry happen, haven't eaten happen. When eaten happen, full happen.
When 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 haven't eaten, hungry happen. So you think these three are the same? Okay. 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 Let me try. Okay. So yeah. So last time I also think that this three should be the same. But actually claim one is logically equivalent to claim two, but not logically equivalent to claim three. Okay? So if you claim that if I ate, then I'm full, this will definitely imply that if you are hungry, confirm you haven't eaten. Because if you eat, you must be full one. But why I say that if I haven't eaten, then I'm hungry is not logically equivalent? Because you are hungry, maybe because of other reasons. Okay? Maybe because not you haven't eaten. Maybe because you do hard work or you do sport and so on. Okay. But if you say that if you ate, then you are full. If you are hungry, you confirm haven't eaten. Yeah. So this is logic. Okay. 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 Next. Okay. Next. This one. Okay. I picked some name here actually from last time. So maybe I can add a few things and know more of you now. So let's say we take our set. Or if you have question, you can ask from previous slide when I'm writing here. So I got a few names here. You're Jen Chuan, right? And then I know the sleeping guy, Liang. Okay, Liang. Okay, Liang. Okay, so let's talk about this rules of inference for quantified statement. Okay, so what does this mean? So first we will introduce this universal instantiation. Okay, what is this? For example, let's take an example. Okay, so example, I make a claim for every student in the Thursday group. Okay, you can imagine yourself. Just imagine yourself. Just that I can't include all the name here. Just imagine yourself. Okay? So every student in the Thursday group passes discriminant. Okay. So once I make this statement and this statement is true, then I can say that okay, first, okay, let's say these are the group of people I have now. So imagine you are one of them. Okay, yourself is one of them. So I can say simply pick one. So I can say Caleb passes Discrete. So I can infer that Caleb passes in Discrete and Zoe passes Discrete. So I want to check next. Jordan, maybe Jordan. Jordan is in the Thursday group, so Jordan passes Discrete. Then Chuan also passes Discrete. On also passes Discrete. Liang, Liang pass or not? He everyday sleep or not? I don't know, but pass lah, pass lah, pass lah. I hope it pass. Passes Discrete. Okay, so this is universal instantiation. Okay, second one, universal generalization. So if your statement is true for any C, then you can make the statement that every X in the domain is true. So this is the reverse process. So in real world, you will check the thing inside your set, the thing you care about, check all of them whether it's true or not. And then for example, let me see, I pick one student from here. Okay, I pick Liang. Okay, Liang passes. Okay, good, very good. Jordan also pass. And then Zhenchuan pass, On pass, Zoe pass, Caleb pass. So since all of them pass, then I can make a statement that every student in the Thursday group passes this reference. Okay, so this is a reverse process. How about there's this C? There's this as student in the Thursday group passes the discrete math. Implies what? There's some student or there's at least one student that passes. Okay. So if I said there's one, that means you can find one in this group that passes. Fourth, if someone in the group passes, then that means there's this one guy or person that passes. Yeah. Say again. Is from what? Yes. Yes. You can think like that. Yes. Yes. So instantiation is like instant. Yeah. Instantiation is like a specific example. Generalization is like you yeah, look it at inside a group. Yeah. So you generalize it. And then instantiate is a specific example. Okay. Okay. Oh, finished 10 minutes earlier. So any question or you want to do some exercise that I assigned just now? We can do it now, or you have some question we can discuss now. Because first class I did almost everything I passes the time. So some of it I left as an exercise. So do you want to do some exercise or you want to ask question? You want to go to next week material? Rules you mean for this one or this one? This one? How to show? How to show? How to show technology? Okay, maybe it's a good question. Maybe you spoil my exam question. No, I just kidding. Okay, which one you want to see? Pick the hardest one. Huh? What? No, just kidding. Just kidding. Just pick one. First one, okay. So let's try. So, hey, what's your name again? Fei. Fei. So P plus Q minus P minus Q. Sorry. Okay. So you want to see how is this topology? So this is the general method. Just draw the truth table. P Q P implies Q P implies Q and P implies Q implies Q. Okay. So I put true, 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 false, false, true, false, false. So P implies Q is what? True. P implies false. That's my true. True, false, my false. P and P implies Q is true, 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 false, 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 true, false, false, true, false. And then the whole thing implies P. So true implies true is true. False implies false is false minus true is false is. Yeah. So this column here is always true. Yeah. But of course, in real life, it's saying that if you have this and then you have this, and then you obtain Q. This is true. Yeah. You okay? Got Fei, huh? Got Fei. Any other question you want to try? Exercise? Bonus? Oh, bonus. Next week quiz on. Bonus, bonus. Okay. Other class don't have this one. Want to ask exotic question? Maybe build one quantifier question for me also can. Like something to be just say by different is a function. Any question? Any other questions? Any other questions? Mm, Let's see. Hey, I think I forgot to mention one thing. Let me come back a bit. Here. So here I want to add something here. So, wait, is it here? No, not here. Here, I want to add something here. So when it is px, we call it a unary predicate. In general, you have maybe n-dimensional, so you have n variable. And you call it an n-ary predicate. So you have two, you have binary. You have three, you have tertiary. University is like one university, so you want tertiary education is like third. In general, you have n. More question? Questions. Only asking question you can improve. Human improve because of questions. If you don't ask question, then the improvement will be stagnant. Ask question. Yes. What do you want me to repeat? Which part you don't understand? All of this? Maybe okay. I think okay. If you say you don't understand all of this, right? Okay, you see. So you listen, how you use logic here. So she said that she doesn't understand all of this. So for all, here got four part, right? For all, she don't understand. So how we deal with this? So we deal it one by one, right? Okay. So since you said all of them, I simply pick one you also don't understand. So let's say I pick first one. So I asking you again. So for first one, what yeah. Okay, you say you don't understand, right? So first one. So let's do first one. So first one, universal instantiation. Okay, first of all, do you understand what this means for every x px? For every x px mean for all x, for every x, and for all x, px is forward x in the domain px. Okay, since Since it is true for all x px, so then I can pick one. So I can pick one. So I can pick x equals c. Okay. So in this example, I say that for every student in the Thursday group passes the course. So in particular, a person here will passes the course. Okay. Does it make sense? Does it make sense? Okay. So so for the others, okay. So 1 and 3 is similar, right? 1 and 3 is similar. So this the quantifier is the existential. So as for existential, you just find there's some, not for all, but there's one that works, at least one. And then 2 and 4 are paired together. So 2, you have to check for every x in your domain. Okay. If it is true, then you can make the general statement. Okay. But for 4, it just has to be true for one statement. I mean, no, just has to be true for one example and one element, then you can make the general statement that there exists one. That's all. That's all what this is all what this table wants to say. Okay, if no question, then we'll break another 10 minutes. Yeah. Not all of them. Okay, you want to make half of them fail, is it? Okay, yeah, so bad. Okay, no, just kidding. Okay, make them fail. Okay, I make them fail. Make this half fail. Okay, then how would I proceed? How would I proceed? How would I proceed? Okay, good. So let's say in a scenario. Okay, she gave me a scenario. Do you care about who fail or not? Or you just want half of them fail? Okay. Okay, we got a new scenario here. New scenario. What's your name is K. K? What's your name again? Max? Okay, Max. MX. Okay, new scenario by Max. Okay, she said she want me to fail half of it. Half. Okay, let me fail. Okay, I simply fail. Don't don't take it into percent. So I make this fail. Under yellow. Okay. Let's say in a new scenario. So white fail. No, white pass. Yellow fail. Okay, fail. How do you make a generalization statement? So you can't say that every student here pass anymore, right? Because I found one guy don't pass, maybe Jordan. Okay. If I want to generalize, there exists. Okay, there exists. What? Okay, let me write. There exists student in the Thursday group. There is part failing the course. Hey, you can write fail. Is it how to spell fail? Don't even know how to spell fail already. How to spell fail? Is it correct? Yes, again. In my dictionary, there's no fail. Okay, so so there exist students in the Thursday group because okay. I also can make another statement. There exist students in the Thursday passing the course. Okay. So both of these statements I can make because I can find a student who pass. I also can find a student who fail. Right. So actually this is quite interesting. Maybe I can change a bit. So can I say there exist students in the Thursday group failing or passing the course? Is this true or false? True, right? Because you can find someone who fail. True, 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 right? There's this student who failed their pass the course. The student. Okay. Actually, I don't know, but there's some ambiguity here. So whether I want the same student who fail and pass, or I have different students who fail and pass. Is there something wrong with the English or not? Huh? What? What do you think? It's good? So you think this is true? So this statement is true. Do you think this is true? So can you explain why is it true? Different student. Different student failing and passing. Is it? Different, right? So different people who are passing, different people who are failing. Student. Yeah, yeah, sure. How about this one? If I change this n to all, true or false? Why? Huh? Yeah, that's okay. That is my question originally. So this question actually allows different students that fail or pass along, or a student that fail or pass. You get what I mean? Huh? Huh? Correct position. I know there's no grammar problem, but am I refer? Can I allow different students that different student? Yeah, yeah. Yeah. So if I allow different students, right, then of course there are students that fail, the student that pass. So it's still true, right? It's still true because I can find students that fail, I can find students that pass. Yeah. Okay. More confused. Huh? Yeah, man, it's okay. Huh? Question. Why you look at me like that? Any more question? Hmm? I said true, I said true. I said true. Welcome to disprove me. True for both. Okay. No question, then we will break 10 minutes and then in 10, 11, 09, come back for tutorial. Thank you. Hmm? refer to what?
I think can be referred to the table.
I will provide. Yeah.
Logically equivalent, we have the symbol of three lines.
Mm-hmm.
Not logically equivalent.
Slash the three line. Slash. Yeah.
What is the difference?
What's the difference?
Universal?
Huh?
Is it like you need to confirm that everything is true, like everything is happening? So
This is for this universal generalization. What do you mean?
for example, last time you give that
Uh-huh.
6%.
Yeah.
If 6%
Yeah.
pass.
Yeah.
So use this first one.
No. First one is start from here.
Right.
First one start here. And then end. And then the okay, this one is this. And then this one will be so this one. So start here and here.
So first
Hmm.
first one is because everyone is
Hmm.
so you just simply pick anyone.
Yes.
Okay.
Mm-hmm.
And then second one is because everyone is passed.
Mm-hmm.
So you have a statement that say everyone is passed.
Mm.
Then one is similar like
Huh?
one is
Yeah, one is similar and three.
so means everyone
Okay, this change to the
one.
yeah. Mm-hmm.
I mean at least one student in the same group has discrete. So at least one.
Yes.
So no matter 2, 3, 4.
Yes.
Yes. At least one.
Yes.
And fourth is here everyone pass. So
Okay, at least one.
at least one.
Yeah. Yeah.
Digest.
You digest. Okay. Oh, okay. Before we start the tutorial section, I think I know where's the confusion. So I didn't write something. I didn't wrote something that I say. Is it? So you confused. So your mind is like keeping with this example, is it? Because I only wrote for part one, and then what I do for the rest is what I say. Okay. So for part one, right? So you start with this. So you look at the orange one. So I start with this statement, and then I have all these statements. Again, this is part one. For the blue one, I start with this scenario, and then I get the ending result. Yeah. For 3 and 4, what I did is I changed this quantifier to there exists. And then there's this, you just need to find one. Again, I didn't write it down, but I just say it out loud only. And then for part 4, you just need to check whether there's some. Okay, I think the scenario here maybe helps just now. So there's this sum, and then you can make the statement there's this. And in yeah, so in real life, maybe you just check 3 of them, right? So you said there exists. But in fact, like this case, all of them pass. So in real life, you can upgrade the statement for the existential to universal. Okay. Universal is more useful, right? So you can apply the universal to everything inside the domain. But there exists. Sometimes you can find it, sometimes you can't find it. So we have a proof like called non-constructive proof for existential. So meaning we can I can show you that there exists one, but I cannot show you how to find one. Okay, this kind of this existential statement. I cannot tell you how to find, but I can tell you it must exist. So yeah. So depend on your situation. Okay, so let's spend 10 minutes, look at the questions and then try out the question. You can discuss with your friends and then we will discuss together at 11:20.
How much? Uh-huh. Are you in the name list? Is it in the name list? Are you in the Moodle? Are you in the Moodle? Yes. Okay. Which one? So you email me for your, you email me for the visa, is it? Yes. Okay. Yeah. Okay. So. Uh-huh. Okay. Mhm. I should just review the textbook. Are you in the Moodle already? Yes. Do you study the last week lecture note? I see the textbook, but I didn't those exercise I did. I didn't see. See.
就是它我觉得它是这个八成
嗯
类似question yes
Have you tried? Have you looked at this section already?
yes
Do you understand?
yes 都买应该平跟手部的
English is not good.
然后都是
Mhm.
definition 是
Mhm.
就是 can't repeat
Cannot remember? No, cannot remember. You just refer. Just refer. So, do you understand this example? You understand? You understand? So, make sure you understand these examples. And then, if you don't understand the example, you read the definition again, and then you read the example again. And then you try the example or the example. Try if you can work it out yourself or not.
these are okay
Huh? These are okay?
yes
Okay. Oh, this okay?
okay
Yeah. And then try the tutorial question I gave you. Have you tried this question yet? Yeah. Try this question. And then try the question, similar question to this in the textbook. So this textbook has solution to odd number question like 1, 3, 5, 7. So because these are given even, so you can work on the first question, third question. So there's solution here. At the back, you can compare. Have you downloaded the textbook already?
Yes.
Yeah, so there's the solution at the back. Solution. Yes, solution. So you can see whether you do it correctly or not.
okay
For the yeah. And then if you have any more question, you can come to my office hour or email me. Yeah. Try workout. You already done this question yet? Have you done? Yeah, you should try this question. And then first thing to learn this course is you need to understand the example. All the example I gave you need to understand. And then all the exercise I asked you to do, you better do. Okay. Yeah. There's a lot of content in this class, but we only have one day of meeting time, so I can't do everything.
thanks
Yeah. So you have to. Okay. Hello.
Hello. Okay. Let's see what we've done. So first question, we want to show that the double negation law, not P is P. So what you do, you just draw the truth table, right? So you write out what is P, what is not P, and then work out what is not P, and then you'll see that not P and P have the same true values. Okay. We'll mark one. Next one. So 1.3.10. So you want to work out the rephrase the implication into the disjunction and conjunction. So the key here is to know how to change from the arrow to the disjunction. Okay. And then apply the definition, right? And then not P, double negation rule become P. Okay. If you have done, you can check your question. Check your answer. Yeah. In general, you should explain like each step what happened. Maybe you use the De Morgan's law. Use by definition. Implication together. So then you know what happened in every step. Okay. Double equation. Okay. One question, then next. So next, so that this is a tautology. So there are how many variables here? 1, 2, 3. So in total, we have 2 times 2 times 2 to the power 3 possibilities. Okay. And then show that it's a tautology. So we need to check that the last column is all. The compound proposition has the only true as the true value. Okay. Okay. Any question? No? Next. Next. So let x be number in the integers. So the statement is the sentence is x plus 1 greater than 2x. Okay. So Q0 is true or false? True. Because 0 plus 1 is greater than 2 times 0. Q minus 1 is true or false? True also, because 0 is greater than minus 2. Q1 is true or false? False. Right, because 1 plus 1 greater than 2 is false. So 2 is equal to 2. So next question is, there exists x qx. Okay. So there exists an x such that this is true. It's true or false? True. Because A and B already tells you just take 0 or minus 2, minus 1, sorry. Minus 1. Right? For every x, qx, true or false? False. False. Why? You can look at C, right? So you just take Q1 and then 2 is equal to, not greater than 2. Okay, so it's false. Does this an x, not qx, true or false? True. Why? You also look at C. And these two are actually like negation of each other, right? So you negate for every, you become there's this, and then you negate the sentence. For every x, not qx, true or false? False. You can also look at from A and B. So G is actually a negation of D. So let me write out. So E is a negation of F, and D is the negation of G. And similarly, negation of E is F, and then negation of D is G. What else then? Yeah, so in mathematics, right, when you see this A, B, C, D, sometimes usually they have connection. Okay. So we'll ask you to do the first part first, and then I'll do the next one. Okay. Okay, next. So negate for every x, 2x minus 2 less than x and x less than 3. So use the De Morgan's law. So for every become then this, right? There's this and then not the conjunction. So you are noting a compound proposition. What law do you use? What law do you use? De Morgan's law. So the conjunction become a disjunction, and then you negate both statements. Okay. The B should be the same, so you negate for every become there's this, and then n become or and greater or equal to become less than, and then less than become greater or equal to 5. And then similarly C, there's this, negate there's this become or n become or x greater than equal to become less than x greater than 1. So negate, does this become for every, and then something wrong here. Let me put it back. So this is less than equal to this one. This is greater than equal to 1. So let's check. Okay, let's check the true value of this guy. So part A, true or false? True or false? True or false? True. Okay, why is it true? Find me the x. Find me the x. X to be what? Right? 4. Okay, 4. 4 works because 4 is greater or equal to 3. Although it's not less than equal to -2, but this statement is an or. Okay. So you also can take x equal to -2, which is less than equal to -2. Okay. How about B? B, true or false? True. Why? -1. Take x equal to -1. Yes, can. Although it's not greater than equal to 5, but this is an or, so one of them true is okay. C, true or false? False. Why? 0. So 0. What happened to 0? So 0, no, cannot get 0 because 0 is greater than 1. Wait, let me see. 0 is less than 1, and then 0 is greater than -4. Okay, let's do a 0 can. So you have to prove both wrong, right? So to prove this is wrong. How about D, true or false? False. Why? Huh? Why? If you say it's false, you have to find an x for me. Huh? -2? -2. -2 is greater than -5. -2 is less than -1. Okay, yeah. Okay. Cool. Any question? No question? Question. And next. 1.4.52. So show that for every x, px, or for every y, qx is not logically equivalent. Yeah, not logically equivalent to for every x, px, or qx. So to prove that it's not logically equivalent, you just need to give me an example. Anyone have any example or not in their book, in their working? Anyone try this question? Anyone try it? And let me know if you try. I'll say mine. So let x be in the real number. Okay, qx will be x less than or equal to 0. Px will be less than or equal to 0. Qx will be greater than 0. So this sentence is true because for every x, it is either positive or non-positive, right? But if you split them out, it's false. Can you see why is it false? Can you see why is it false? You can pick x to be 1. Okay, so 1 is greater than 0. You can pick x to be -1. So -1 is less than 0. Okay. So when you split them out, they are false. So the textbook example is you have integer. And integer are either odd or even. But if you split them out, then it's wrong. Right? You can always find something is odd, or you can always find something is even. Make sense? Understand? Cannot. You must ask not ask question. Yeah, but why are not? Did you get what I explaining also? No? No? Huh? Cool what? Oh, cool. Wait. So what's wrong? What's wrong? Wait. Let me bring this. Okay. First of all, do you know what is this question asking? No, right? No. Wait, let me see. What's going on here? Okay. So okay. So actually this question start from here, right? So I write it bigger maybe. So this question is like this. Okay. So for every x, okay, you want this statement to be true. So this 2x should be the same x. Okay, every time you do. So in your mind, distribute, right? Distributivity. So can I look at this? I distribute the quantifier into it. Are they the same or not? So the naive question is, are they the same? Same or not? Not that here, these two have nothing to do with each other now. Okay? Because this guy controlled by this guy, this controlled by this. You don't think this x although they are all x they are different ones. Okay? They are different x. This just placeholder, meaning I also can write px x p for every y. I also can change one, never mind. But in this case, you cannot change this to px y. Okay, this is different story already. So this is not allowed. Okay. So in your mind, these two should be independent to each other. Okay. So what I gave just now is, if I consider a case where, so this is my example, counter example. So if you look at x, so every time I have to specify a domain, right? So it's my real number. So real number is either positive or non-positive, right? This one you agree or not? Agree or not? This one agree or not? Agree? Agree? Agree, Why agree? Real number. So real number, if you pick one real number, it's either fail in this category or fall in this category, right? Okay. But if I split them up, so I'll be really clear if I split them up. So I change my variables like this. Okay. So is this true? So is this true or not? True? True, man? False. Why false? Huh? Why is it false? So why is it false? So this is false. Why? By what? Oh, by taking one. So take x equal to 1. 1 is greater than 0. Okay. This one is also false. Because I can take y equals to -1. Okay. So that means this guy false, although this guy true. So they can't be logically equivalent anymore. Okay. Right. Okay, I'm sorry. I'm still confused. What may be? Confused? Ask lah. Ask. Others also confused. Just they don't want to say only. You okay or not? I need time, huh? Okay, I'll give you time. Okay, I'll give you time, huh? Later, if you think of some question, ask again. Yeah. Because if you guys don't ask, I don't know what I mean. I don't know what you don't understand about. So make sure like you ask, and then I will address your question, and then we will see what's wrong. Okay. Yeah. What do you mean? Uh-huh. Uh-huh. What then? Huh? Where's the De Morgan? Because I didn't see negation here. De Morgan need negation. De Morgan's need negation. What are you trying to do? Hmm? Okay. If you try out, you can ask again. Yeah, De Morgan, you always need negation first to use De Morgan. Okay. 1.5.4, a bit. You can try for one. So you see, one thing to notice here is they sort the order of y and x. Yeah. And then they sort the quantifier. So see, so let's see, maybe compare, let's see, which one? Okay, let's see C and E. Okay, C and E may be more interesting. C is for every x, there's this y. And then for E is for every y, there's this x. So x is the student. So for every x come first, so every student has taken at least one computer science course. Okay. But for E, y come first. So this means I will have to fix the classes first. So every computer science courses has been taken by at least one student. Yeah. So here I want to demonstrate that the order of x and y is very important. And then the order of the quantifier is also important. Okay. Okay. Yes. And next. Wow, 6 minutes left. And this is the last one. Again, this one will be more interesting a bit. Okay, let's try. For every x, there's this y, such that x squared equal to y. Is it true or false? So, okay, first of all, x and y, I have to tell you what the domain is. So the domain is in real. So for part A, is it true or false? True. Why? You just take y equal to x squared. Of course, you need to check whether this is in R or not. Yes, it is in R because multiplication of R is still in R. R is closed under multiplication. B, true or false? False. Why? Hmm? S is less than 0. What do you mean? Huh? What? You just read my answer. Why is it false? Hmm? Why is it false? Huh? So Okay, so yeah. So maybe you can say that x when -1, there's nothing square to -1, something like that. Right. So let's see. So y equals 0 is not equal. Can I say that? Okay, yeah. So the argument is the argument is when you take x to be negative, there's no y that's square to negative. At least for y in R. Okay. There's nothing that's square to negative. Okay. Take x negative. Okay, but this is not the case for complex number. Okay. So for complex number you can do it, but for real you can't do it. Okay. See? True. Why? True. You take x equal to 0. So 0 times everything is 0. D, true or false? False. Why? Because the addition of real number is always commutative. So yeah, you can't find x and y such that they don't add to the same number. E, true or false? True. Why? Huh? Why? True. So true mean what? There's this. You need to find me a y. Okay. You need to, for every x I give you, you need to give me a y. You take the inverse. Yes, you take the inverse. But why the inverse exists? Because x is not 0. Okay. If x is 0, then this doesn't exist. So it's undefined. So since x is not 0, then the inverse exists. So for every x I give you, you give me a y such that they multiply to 1. Okay. F, true or false? True or false? True or false? False. And false. Well, false to this statement is a bit harsh. So you need to, for every x, you need to find me a y such that y is not 0 and xy is not equal to 1. Okay. So for every x, okay, my strategy is I take y equal to 2 over x. Okay. So that when I multiply them together, I get 2, which is not 1. Okay. In this case, you got a lot of answer. You can get 2 to be 3 over x or 100 over x. All of them multiply not equal to 1. Okay. Next, for every x, there's this y, x plus y equals 1. True or false? True. You just take y equal to 1 minus x. Okay. For every x, you need to produce a y. So whenever you see these, right, the existential. If it is true, then you need to find me one. Okay? You need to find a y for me. H, for h, there's this x, there's this y, such that x plus 2y equals 2 and 2x plus 4y equals 5. So this is actually simultaneous equation. So you can solve it first. You solve it, and then at the end, you found contradiction, 0 equal to 1. So there's no x and y such that 1 equals 0. Okay. Contradiction. Okay. 1. I. So for every x, there's this y, x plus y equals 2, and 2x minus y equals 1. So you also solve this simultaneous equation, and then you only found x equal to 1 works. So x must be equal to 1. So it doesn't work for all x. Okay, so it is false. Okay. J, for every x, for every y, there's a z equals to x plus y over 2. True or false? True. You need to find me a z. So how to find the z? Z is just x plus y over 2. So why this work? You need to check whether this is in your domain or not. So because real number is closed under addition and also scalar multiplication, which means if you add them together, you are still a real number. If you multiply by a real number, you are still a real number. So true. Yes. What? Too fast. 11:50 now. But if you want to ask question, I can stay back for. Yeah. Because we are getting fast. Yeah. If you have question, I can stay back. If you have classes, you can leave. Okay. No worries. Bye. Thank you. Yep. Mm-hmm.
Because as for this, the using
What more?
I can understand all you can like
Let me stop.